Hello, I've got a demo for you today and a little bit of thinking about the demo. So I've got this track, I've got a car, and I've got a cannon mounted on the car. That's what this black thing is. If you look down the barrel of it, you can see a circular indentation there. That's where this yellow ball goes. You may be able to see it. The ball will be a little bit hard to track on the video, but you should be able to do it, I think. So what happens is I put the ball there in the launcher, I push it down, and it clicks at the bottom. It's a spring-loaded thing, so it sits on a spring that's compressed, and then when the cannon is fired, the spring releases and shoots the ball up. And it shoots up, straight up, so perpendicular to the orientation of the track right now. The first thing I'm going to do is hold this car steady and fire the cannon while the car is stationary. And just to get a sense for what works here. And before I do that, make a prediction for what's going to happen. So if I fire the cannon, then where will the ball go and where will it land? So if you need to pause your video for a sec to think about it, do that. Okay, so I'm going to load the ball and I'm going to fire it. Let's see what happens. Okay, so if you could see that, what happened was the ball went straight up and turned around and came back down. So that makes perfect sense. It's just like throwing a ball straight up and down. It stays kind of in one dimension, just on a line, straight up and down. The more interesting question is going to be what happens when this cart moves? So if I start rolling the cart around before I fire the cannon, what happens? So that's what I'm going to try next. So I've got a little thing here. I don't know if you can see it, but there's a little device here that will trigger a photo gate on the front side of this. The way I fired the cannon was there's a tiny little photo gate right in the front. You might not be able to see it on the video, but there's a little trigger for that photo gate right here. So if I roll this by while the cannon's depressed, the ball should fire out of there because the photo gate's the trigger for the cannon. So let's try it. So what I'm going to do is I'm going to load the cannon, send it this way. It should fire when it gets here, and the cart will keep rolling. And I'm going to pose the same question to you. While that's happening, if the cannon fires while the cart's rolling, where will the ball go and where will it land? As a reminder, the cannon just fires vertically, that is perpendicular to the track. So if you want to pause your video and make a prediction for what you think is going to happen, reason it through. Try to come up with some physical reason that supports your idea. So what physics would explain why you think the way you think. So pause your video if you want and come up with a prediction. Okay, so let's try it. I'm going to load the cannon. Let's try it. I'll try it relatively slowly at first. Let's see what happens. Okay, so wait, let me try that again. But you'll notice that the ball just landed right in there. So let's watch again. Okay, so same thing happened. So in both cases, the ball landed back in the position that it launched from. So what's going on there? I'm going to roll it faster now. Let's see if the same thing happens. So if I roll it faster, will the same thing happen? Was it just a fluke? It landed back in the launcher again. One more time to see it. And it landed back in there again. So what's going on? Both times, whether the car was stationary or whether it was moving, the ball landed back in the launcher. So what's going on with that? We're gonna now unpack this a little bit, but if you want, take a minute to kind of reason out what's happening. Was your prediction accurate or not? And what does that tell you about the physics that's determining the way this ball moves? So let me switch over to my iPad. Okay, so I've got a little diagram of the demo here. So here's the car, and let's say it moved from there to there while the ball was in the air, and the ball took some trajectory like this. And as we saw, the ball landed back in the cannon on top of the car at the end. So we know whatever happened, the ball landed in the cannon again. And the question is why? Why did the ball land back in the cannon? The short answer to that question, I guess I need a question mark. The short answer to that question is that the ball always had the same velocity as the car. If the ball, in the x direction, I should say, if the ball had a different x velocity than the car, it wouldn't end up in the same place as the car. So whatever it was doing in the x direction had to have been the same as the car. So this is maybe an important point, because the x velocity of the car was always the same So let's think through what that means specifically in this case. So the car, I pushed the car, and then the car was rolling without any other thing pushing it. So we can assume that basically it's going at constant velocity. So the car has got some velocity, let's call it Vx, constant velocity as it's doing this. It travels some displacement in that time. And we know that in the same amount of time, the ball travels the same displacement because it ends up in the same place where it started. That means that the ball has to have a constant velocity Vx2. Why does it have that? Well, it was moving with the car to start. So before the cannon was launched, the ball had to have the same velocity as the car. Otherwise, it wouldn't be moving with the car. When the ball's launched, a lot of stuff is happening to the ball, and its velocity is changing, but the part of its velocity that points in the x direction isn't changing because the only forces that are accelerating the ball are up and down. So there's the spring that pushes the ball up, straight up, perpendicular to our motion of the car, and also gravity that starts to accelerate it down once it's left the spring. That creates that parabolic motion of the ball. But that's also perpendicular to the direction that the car is traveling. So what that means is that both, in this case, both the car and ball move at Vx in the x direction for the whole time, even though the velocity in the y direction for the ball is changing. That doesn't affect the x velocity for the ball. And this points to a really important concept, that the x and y components of motion are independent of each other. Even though the ball's y motion is way different than the car's y motion, because the car isn't moving in the y direction. The x motion of the car and the ball is the same, because there was nothing changing the x motion of the ball here. All of the changes to the motion happened in the y direction. And so we can treat x and y differently. So we have this equation. So displacement equals initial velocity times time plus 1/2 a t squared. And we've established this for one dimension. But you can use that for any coordinate you want. So for example, here, I've got my x dimension going forward. So if I were writing the displacement for the car, so the x displacement for the car is equal to the initial velocity of the car. That's what I called v sub x times time, plus the 1/2 the acceleration of the car times time squared. But there is no acceleration for the car because it's just pushed and it's moving along a relatively frictionless track. So this is the displacement of the car over time. Just a linear increase in displacement because of constant velocity. But the same thing's true for the ball, because if I write the x displacement for the ball, well, the initial x velocity of the ball when it leaves the car is still vx. That's the velocity in the x direction. We don't care about the velocity in the y direction because we can treat the x coordinate and the y coordinate independently of each other. So the y coordinate has nothing to do with the x equation, times time, plus 1/2 acceleration times time squared. Even though the ball is accelerating as it's going through this trajectory through the air, as it leaves the spring and is affected by gravity and stuff, that acceleration is only in the y direction. It's only up and down. It's not horizontal. And so there is no x acceleration. And to be really clear in this equation, if I'm in this equation, if I'm talking about an x displacement, I'm talking about an initial velocity in the x direction and an acceleration in the x direction. And so the ball's displacement looks exactly like the car's displacement in the x direction. Now, I can use the same equation for the y coordinate. If I wanted to, it looks exactly the same, but I would write it like this. So I'd say the change in the y position is equal to the initial velocity in the y direction times time plus 1/2 the acceleration in the y direction time squared. So if we did this for the car, then the initial velocity in the y direction for the car is 0 because it has no velocity up or down, and it's not accelerating up or down either. So the y displacement for the car is just 0. It does not move in the y direction. And I can do the same thing for the ball. So if I want to do delta y for the ball, now this is where things get a little complicated. So there was, if we take our time to start when the ball just leaves the cannon here, then there was some y velocity. And I can, let me say that it left the cannon with some, v y. Let me call it vy. That's the initial velocity that it left with, and I'll call it vy I, to just be clear that that's an initial velocity. So v in the y direction initial times time. And then there definitely was acceleration in the y direction too. It's gravity. And that acceleration points down, so it's negative in this coordinate system. So minus 1/2 g to denote the acceleration of gravity, t squared. That's the displacement of the ball in the y direction as a function of time. These 4 equations are true, and they tell us everything we need to know about this system, at least the motion of this system, from the time the ball left the cannon to when it returned to the cannon. And the only thing that really determined whether the ball landed back in the cannon or not was the x position. And we saw that at all times, the displacement of the car is equal to the displacement of the ball. So no matter what the ball is doing, no matter where it is vertically, it will always be positioned right above the cannon. And when it falls down, it'll land right in the cannon too. And this equation looks very similar to the one-dimensional motion problems we've solved for throwing rocks up, for example. Just any motion of something moving under the influence of gravity. And the big idea here is that we can break the X coordinate and the Y coordinate apart and deal with them separately, so that the acceleration in the Y coordinate only affects this Y displacement and does not affect the X displacement. So that's the big idea here. And that's, I think, what the demo illustrates. And we'll keep going with this idea and expand upon it. But I hope that was helpful. Okay, bye.